Hi, I'm Yuezhou from Northeastern University. Today, my topic is field caching networks. This is a joint work with Yuanyuan, Qian, Stratis, Ioannidis, and Edmund here. To start with, I want to mention that caching and resource allocation problems are ubiquitous. They appear in CDN, cloud computing, Internet of Things, content-centric networks, etc., and etc. Of course, we won't be able to study all of them. So what we do is that we consider a general cache network with arbitrary topologies. In these networks, user nodes generate requests for content items with certain request rates lambda. Requests are then routed through the designated server to be served. And in this network, nodes have caches with finite capacities. We can store content items in them. In this case, request may terminate earlier upon the cache hit. After that, content is sent back over reverse paths. We can further associate each edge with a cost, which is the cost to transmit a content over this edge. Then in this case, because of intermediate caching, we can save the cost of these two edges. Then we define caching gain as the routing cost reduction, which is 4 plus 6 in this case. Then the caching gain rate is the request rate times the caching gain of this request, which reflect the expected caching gain of the request. Then, given such a cache network, how should items be allocated to the caches? What is the optimal caching strategy? Several existing work study the cache strategy that's maximizing the overall caching gain rate. There are several advantages of this objective. First, it captures popularities and the routing cost at the same time. It captures the popularities by request rate lambda and captures routing cost reduction by caching gain. It has been shown that in a general cache network, algorithms that ignore routing cost can be arbitrarily suboptimal. Another advantage is that the objective function is submodular. So even though the problem is NP hard, we may be able to design approximation algorithms that runs in polynomial time for it. However, all the above listed works do not consider the fairness issue. So in this work, instead of simply maximizing the overall caching rate, we also take fairness into considerations. We want to achieve a balance among the benefits that different requests derive from caching. Several other works study the fair caching problems. They either consider specific fairness notions or make use of the alpha fairity functions, which generalize different fairness notions. They study different utilities or objectives. Some study the fairness of hit ratio. Some study the fairness of storage and fetching cost, of video quality, of throughput, or of delay. However, these objectives do not capture the multi-hop routing cost. So in this case, they may be suboptimal in a general cache network. As an example, requests served with hit ratio 1 at a distant server in reality have a lower utility than requests served locally with a lower hit ratio. So in this work, to study the fair caching problem in a general cache network, we consider the utility of caching gain. Our contributions are the following. We give formal statement of the fair caching network model. We show that the problem is NP hard. And we prove that this problem is a maximization of some modular objective under matrix constraints. So as a consequence, the greedy algorithm produces 1/2 approximation factors, and the continuous greedy algorithm produces 1 minus 1/e approximation factor. We further discuss a stationary randomized strategy, and we introduce a method called L method, which produces this approximation factor, and it's actually better than 1 minus 1 over e for some utility functions. Then we do extensive evaluations. We show the performance of our algorithms and the different network topologies, and we give an analysis for the effect of variables. So let's first discuss the problem formulation. A cache network can be represented as a directed and bidirectional graph GVE, where V is the set of nodes and E is the set of edges. Each edge in this network has a cost, which is the cost to transmit the content over this edge. Each node V has a cache with finite capacity CV. We let capital C as the catalog of equally sized content. Then for each node V and content I, we let a binary caching variable XVI, indicating whether content I is stored in the cache of node V. Because of the finite cache capacity, we have this constraint for each node V. Then we let matrix X as the global allocation strategy or the global caching strategy. We assume that for each node content I, there exists a set of nodes that permanently store I, and we call them the designated servers of I. A request is a pair IP such that I is the requested content item, and P is a path all the way to the server. We say requests are always satisfied because in the worst case, they can be satisfied at the servers. We let R as the set of all requests, and each request has a request rate lambda IP. We say the worst case routing cost is the cost to download the content item from its server. And in this case, it is 6 plus 4 plus 3 plus 5 in this form. And because of caching, this cost can be reduced. In this case, it will be 3 plus 5. We then define caching gain as the routing cost reduction, and we denote it by function f. To study the fair caching problem in this cache network, we consider the so-called alpha fair utility functions, which generalize different fairness notions. As alpha increases, these utility functions emphasize more of fairness. Then the caching gain rate is defined as the request rate lambda IP times the caching gain FIP. And we consider the utility of request as the utility of the caching gain rate of such request. Then the goal of this paper is to maximize the overall utility of all the requests, subject to these caching constraints. And we let D1 be the feasible set of the caching strategy. So this problem is NP hard, even for a special case when alpha equals to 0. Then we talk about our deterministic strategies. They're mainly based on the submodularity of the objective functions. We first show that for all alpha fair utility functions, the utility maximization problem is actually a submodular maximization and a matrix constraints. So as a consequence, we have two polynomial time approximation algorithms, the greedy algorithm, which produces a solution within 1 over 2 approximation factor from the optimal, and the continuous greedy algorithm, which produces a solution within 1 minus 1 over e approximation factor, which is better than 1 over 2. We want to introduce a bit more detail about the continuous greedy algorithm. To start with, we have this submodular maximization problem. We then consider its multilinear extension by taking the expectation of the objective function. To do so, we consider the caching variable XVI as random variables with joint distribution mu, and we denote YVI as an expectation of XVI. In this case, we get a non-convex maximization problem of continuous variable y. We then solve it by framework iterations, which produce a fractional solution y. And we then round it by the so-called Pepich rounding technique. we are able to show that with high probability, this rounded integral solution is within 1 minus 1 over e to the optimal solution. Here, X star is the optimal deterministic caching strategy. We then introduce our stationary randomized strategy, which produces a better approximation factor than continuous gradient for some utility functions. So in this scheme, compared to the deterministic, we consider a time-slotted system, and at each time slot, a random caching strategy is sampled from the joint distribution of this product form. We consider a product form because we want to let each node to make their caching decision independently. Then our problem becomes the maximization of overall utility of expected caching gain rates. And we want to decide such optimal distribution. We have this theorem that there exists a polynomial method that produces a distribution within 1 minus 1 e to the power of 1 minus alpha from the optimal in expectation. And this factor is better than 1 minus 1 e for utility functions with alpha smaller than 1. We then introduce such method. We call it L method. We start from this problem and then consider its equivalence. We show that it is equivalent to maximizing total utility over fractional variable 1. Recall that YVI is the expectation of XVI. And this equivalence is mainly because of the independence of XVI for different V. We further consider its convex approximation. We show that the caching gain function f can be approximated by a convex function L. That's why we call this method L method. And the resulting problem, we can show that it's a convex optimization problem. We let the optimal solution for this convex problem as a y star star. And then we run y star star by random rounding techniques, which produce the distribution we want. Then let's go into our evaluation. We first simulate our algorithm over several synthetic and real-world topologies, and we compare them with 4 baselines, FIFO, LRU, LFU, and round robin. We show that the algorithms outperform the baseline caching strategies in all topologies. Then, besides performance, we want to discuss more about why we want to use this fair caching model. We show that content items with different popularities are more fairly stored in the network if we consider this fair caching scheme. We show that in the 4-array balanced tree of head 4, requests are generated at the leaf node and routed to the server, which is at the root. We consider content popularities, follow Z distribution, and the content with smaller index has higher popularity. So in these figures, the height of a bar is a fraction of total cache space used to store a content. For example, here, these 2 bars means that in layer 3, it only stores content 1 and content 2. And each of them occupies 50% of the total cache space in this layer. We can see that when alpha is small, the network tends to only store the most popular content. But as alpha increases, the content with different popularities are more fairly distributed in the caches of different layers. So as a summary, this paper, we discuss a fair caching model based on the utility maximization problem. This problem is NP hard, so we study several polynomial offline approximation solutions. And we show that content items are more fairly stored in the network if we consider such fair caching scheme. A possible future direction is that they are distributed and adaptive algorithms. Thank you.